A black hole does not need to roar to be terrifying. Its most powerful feature is silent a boundary with no surface, no warning light, and no way back. Cross the event horizon, and the universe outside may still shine behind you, but every possible future begins to lean inward. Light can still move at light speed. Time still passes, yet return has quietly disappeared. Welcome to Calm Space Science. If this journey into the hidden edge of space-time pulls you in, a like, a subscription, or sharing this video with someone who loves cosmic mysteries helps this channel keep exploring the strange places where science becomes wonder. Thank you for spending part of your day, or night, here. What time is it where you're watching, and where in the world are you listening from? Leave it in the comments, along with your thoughts on what might truly happen beyond the horizon. Now, let us step carefully toward the edge of the black hole. Far from the bright surfaces of stars, far from the familiar rule that light usually finds a way outward, there is a border in space that does not look like a border at all. It has no metal rim, no burning wall, no visible skin. A spacecraft crossing it would not strike a surface. Dust drifting through it would not spark against an edge. Even light, the fastest messenger in nature, does not meet a barrier in the ordinary sense. Yet after this invisible threshold is crossed, return is no longer part of the future. This is the event horizon, the defining boundary of a black hole, and its strangeness comes from a simple fact carried to an extreme. Gravity is not merely pulling objects across space. In Einstein's picture, gravity is the shape of space-time itself, the deep bending of distance and duration around mass. A planet curves space-time gently. A star curves it more strongly. A black hole curves it so severely that beyond a certain radius, every possible path leading forward falls inward. The horizon is not the place where gravity begins. It is not even necessarily the place where gravity is strongest. It is the place where escape stops being physically available. Outside it, light aimed carefully outward can still climb away. Inside it, even light has no route that leads back to the larger universe. The horizon is therefore a boundary of possibility, not a boundary of matter. It marks the dividing line between events that can still send signals outward and events that remain forever hidden from outside view. The idea begins with the Schwarzschild radius, a size that can be calculated for any amount of mass. If enough mass is compressed inside that radius, the escape speed at the surface reaches the speed of light. Escape speed is the speed needed to leave the gravity of an object without further thrust. On Earth, it is large, but still far below the speed of light. Around a black hole, at the event horizon, it equals light speed itself. Since nothing with mass can travel at light speed, and since even light cannot exceed it, the horizon becomes the last outward boundary of communication. This is why the name event horizon is so precise. It is not just a horizon in space. It is a horizon in causality. Events beyond it can happen, but their effects cannot reach the outside universe. The outside may infer that something fell in. It may measure the black hole growing. It may see gas heat and glow before crossing. But the actual crossing lies beyond all later report. In that sense, the horizon is a quiet form of cosmic privacy. It keeps no secrets by choice, because nature has no intention, but it separates knowledge from existence with absolute firmness. To understand why this threshold is so misunderstood, it helps to begin with ordinary horizons. On a planet, a horizon is only an effect of perspective. A ship can disappear beyond the curve of the sea, yet nothing has happened to the ship. Another observer farther along can still see it clearly. The horizon moves with the observer. It is local, personal, and temporary. The event horizon of a black hole is different. It is not an illusion caused by where an observer stands. It is built into the structure of space-time around the black hole. Once a signal is created inside it, no distant observer can ever receive that signal, no matter how powerful the telescope, no matter how long the waiting. This gives the horizon a strange double quality. Locally, for something falling freely through the horizon of a large enough black hole, the crossing may seem calm. Globally, for the universe outside, the crossing marks a permanent separation. The same place can be uneventful for one path and unreachable for another. The contradiction is only apparent. General relativity often teaches that what happens depends not only on where an event occurs, but on how an observer moves through space-time around a black hole. This lesson becomes unavoidable. From far away, the horizon appears to be a place where time itself seems to slow. Light sent from a falling object must climb out of an increasingly warped region. Each signal takes longer to arrive. Each signal also loses energy, stretching toward redder and dimmer light. The falling object appears to approach the horizon more and more slowly, as though it is being suspended near the edge. In the final limit, the moment of crossing never appears in the outside observer's sky. This is one reason black holes feel paradoxical. From one point of view, the falling object never quite crosses. From its own point of view, it crosses in a finite amount of time. Both descriptions can be meaningful, but neither is the whole story alone. The horizon exposes how time is not a single, universal river flowing identically for everything. It is part of space-time, shaped by gravity, motion, and position. In weak gravity, this flexibility is almost hidden. Clocks on Earth and clocks in orbit tick at slightly different rates, but the difference is small enough to require careful instruments. Near a black hole, the difference becomes enormous. The horizon is where the outside description stretches the fall toward endless delay, while the falling description continues inward. This does not mean that the object becomes physically frozen at the horizon. It does not sit there forever in its own experience, waiting at the boundary. Rather, the light carrying news of its crossing cannot get out in a way that reaches the far universe at a later ordinary time. The frozen image is an optical and gravitational effect, a fading record, not the object's final lived reality. This distinction matters because the event horizon is often imagined as a deadly surface, a cosmic shredder placed at a precise radius. For some black holes, destruction can indeed occur near or even before the horizon, but the cause is not the horizon itself. It is the difference in gravitational pull between one part of an object and another. These differences are called tidal forces. Near a small black hole, the gravity can change sharply over a short distance, stretching matter into a long narrow stream before it reaches the horizon. Near a supermassive black hole, the horizon can be so wide that the change in gravity across a human scale is much gentler at the crossing. In that case, the horizon may pass without a local flash, impact, or warning sign. The fatal region lies deeper inside, where space-time continues to curve toward the central singularity predicted by general relativity. This makes the horizon more mysterious, not less. A boundary that cannot be felt at the moment of crossing can still divide the universe into two unequal domains. On one side, paths may still lead outward. On the other, all future paths lead inward. The black hole itself is not simply a place where matter has become dense. It is a region where the geometry of the future has changed. Outside the horizon, rockets, light beams, falling stones, and drifting gas have different possible futures. Some may fall in, some may orbit for a time, some may escape. At the horizon and below it, the set of possible futures narrows in a radical way. The direction toward the center is no longer merely a place in space. it becomes as unavoidable as tomorrow. This is why common language struggles. Saying that a black hole pulls too strongly suggests that a sufficiently powerful engine might pull back harder. Saying that light cannot escape suggests that light is trying to climb outward but loses a contest. These images are useful at first, but incomplete. Inside the horizon, outward is no longer a future-directed route to the outside universe. It is not that all engines are too weak in a normal space. It is that the geometry of space-time no longer provides an outward future leading beyond the horizon. Every allowed path, including the path of light, remains inside and moves closer to the singularity. The horizon therefore marks a change in the map of possible cause and effect. It is a frontier drawn not by material substance, but by the deepest speed limit in physics. Nothing outruns light. Nothing sends influence faster than light. So when space-time bends until even light's future cannot point outward, the boundary becomes final. Yet from far away, the event horizon is also the visible absence that gives black holes their shape. A black hole cannot be seen by reflected light, because there is no surface to reflect it. It is detected through its influenced stars orbiting an unseen mass, gas heating as it spirals inward, jets driven from violent regions outside the horizon, gravitational waves released when black holes merge, and the shadow formed when glowing material surrounds darkness. The darkness is not empty in the simple sense. It is a region from which no light reaches the outside. Around it, matter can blaze with extraordinary energy before disappearing from view. The event horizon itself remains mathematically sharp and physically silent. It is the edge of the observable story. The most haunting feature of this boundary is that it is ordinary and impossible at once. Ordinary, because a falling object may cross without noticing a local surface. Impossible, because after crossing, every signal it sends belongs only to the hidden interior. The horizon is not the end of physics, but it is the end of outside access. It forces a separation between what exists and what can be known from afar. It turns the black hole from a dense object into a space-time region with a one-way edge. At that edge, the universe does not tear open in spectacle. It simply changes the meaning of future. Outside, stars continue to burn, galaxies drift, and clocks keep their distant rhythm. Inside, all roads bend toward a place where current theory becomes strained and incomplete. Between them lies the event horizon, calm, invisible, and absolute. A boundary without surface where the familiar promise of return quietly disappears. A black hole begins as an error in ordinary intuition. The name suggests an opening, a hollow place, a drain in the fabric of space. Yet the physics points in a different direction. A black hole is not a tunnel cut through the universe. It is a region where mass and energy have shaped space-time so severely that the routes normally available to matter and light are transformed. The deeper lesson comes from general relativity, where gravity is no longer treated as an invisible force reaching out across emptiness. Gravity becomes geometry, planets, stars, dust clouds, and light all move through space-time, and mass tells space-time how to curve. Space-time then tells matter how to move. In weak gravity, the older language of pulling and attraction still works well enough. A stone falls to Earth, the moon follows its orbit, a comet swings around the sun and returns to the dark. Beneath these motions is a quieter structure. Objects are following the straightest possible path through a curved four-dimensional landscape. Those paths are called geodesics, the nearest equivalent to straight lines when space and time are bent together. Near Earth, the bending is gentle. Near a neutron star, it is fierce. Near a black hole, It becomes so extreme that the geometry does something ordinary experience never prepares for. It changes the range of futures an object can have. The collapse that forms such a region begins when a massive star can no longer support its own core. While it burns nuclear fuel, outward pressure from heat and radiation resists the inward pull of gravity. When that support fails in a sufficiently massive core, matter falls inward, density rises, and known forms of pressure may fail to stop the compression. If enough mass is trapped within its Schwarzschild radius, an event horizon forms. From outside, the result is often described as matter compressed into a tiny volume. That is partly true, but it does not capture the deeper change. The collapse does not merely create a dense object, it creates a region of space-time from which no future-pointing path escapes. This is why the event horizon cannot be understood as a normal surface. A star has a surface because matter stops there, or at least changes sharply enough to give the object a visible boundary. A planet has ground, ocean, or atmosphere. Even a gas giant has layers where pressure and density change. A black hole's horizon is different. It is a mathematical and physical boundary in space-time, defined by the paths light can take. Light outside the horizon may still move outward if it is aimed properly. Light at the horizon can, in a limiting sense, remain on the boundary. Light inside the horizon cannot increase its distance from the centre in a way that leads back to the outside universe. The horizon is therefore not made of material. It is made of the failure of outward futures. Geometry has tilted the available paths until escape is no longer among them. This tilting can be understood through light cones. At any event in space-time, a light cone describes the possible directions that light can travel, and, because nothing outruns light, it also defines the limits of every possible cause and effect. Outside a black hole, the future light cone still opens wide enough that some paths lead away from the black hole. A rocket with enough power could depart. A photon aimed outward could eventually reach distant space. Closer to the horizon, the cone leans inward. More possible futures lead toward the black hole. Fewer lead away, and escape requires a path increasingly close to the path of light itself. At the horizon, the outward edge of the cone lies along the horizon. Inside it, the entire cone points inward. This is the geometric heart of the event horizon. The problem is not that an object lacks sufficient strength. The problem is that the future direction available to all physical motion has been turned. Even a beam of light, sent outward with perfect aim, still moves towards smaller radii in the only future it can occupy. The phrase smaller radius can be misleading, because it sounds like a direction in ordinary space. Outside the horizon, moving inward or outward is a matter of choice, motion, and energy. Inside the horizon, the radial direction toward the centre takes on a role more like time. Outside, time advances and cannot be reversed by any ordinary action. Inside, the path toward the singularity has this same unavoidable quality. This is one reason descriptions often say that space and time exchange roles inside a black hole. The statement is not a simple swap, and it should not be pressed too casually, but it points towards something real in the mathematics. The coordinate that once described distance from the centre begins to behave like a one-way direction into the future. The singularity, in the classical picture, is not merely a point waiting somewhere below. It is a future boundary. Avoiding it inside the horizon is like avoiding next week outside the horizon. Motion itself has been redefined by the shape of space-time. For a distant observer, this geometry reveals itself indirectly. Gas falling toward a black hole may form a disk, because angular momentum keeps the material circling as it descends. Friction, magnetic fields, and collisions heat the gas until it glows across high-energy wavelengths. Some black holes launch powerful jets from regions outside the horizon. guided by magnetic fields and rotation in ways that remain actively studied. None of this light comes from inside the event horizon. It comes from matter still outside, from the last visible environment before the one-way edge. The black hole itself remains dark, not because it is an empty absence, but because the geometry inside the horizon prevents light from returning. The darkness is a statement about paths. The surrounding brightness is a statement about violence outside the boundary. Together they create the strange image of a black hole as both hidden and revealed, invisible in itself yet outlined by the universe reacting to it. The event horizon is less like the rim of a pit than the edge of a possible map. Some routes loop around, some skim close and escape, some cross inward and never return. The black hole is therefore not only an object but a rearrangement of the directions available to the future. This rearrangement grows from mass, but mass alone does not explain the feeling of strangeness. The same total mass can have different effects depending on how tightly it is packed. The sun curves space-time across the solar system, holding planets in orbit, but its radius is far larger than its Schwarzschild radius. If the sun could somehow be compressed inside that much smaller radius without changing its mass, the planets far away would not immediately feel a stronger gravitational pull. At their distances, the total mass would be the same. What would change is the near region, where the surface of the sun would no longer exist and an event horizon would replace it. The black hole's extraordinary nature comes from concentration. It is not mass alone, but mass enclosed tightly enough that space-time closes escape routes around it. This point softens a common fear. Black holes do not roam like cosmic vacuum cleaners, swallowing everything across limitless distance. From far enough away, their gravity behaves like the gravity of any other object with the same mass. A star orbiting a black hole can remain in orbit for immense spans of time, just as planets orbit the sun. The danger grows where paths pass close to the horizon, where geometry becomes steep and ordinary choices narrow. Black holes are not magical holes in the universe. They are precise consequences of gravity carried past a threshold. Their power lies not in endless reach, but in the fact that within a certain boundary, the future is no longer open in the same way. The more carefully the horizon is considered, the less it resembles a place and the more it resembles a rule. It says that there are regions of the universe whose events cannot send messages outward. It says that space-time can be shaped so strongly that light itself has no outward future. It says that gravity, when understood as geometry, can do more than make objects fall. It can decide which directions still exist as possibilities. At the event horizon, the black hole is not grabbing with hands or dragging with ropes. It is altering the stage on which motion happens. Beyond the boundary, the paths are still smooth for a falling object, but their destinations have changed. This is the quiet power of the horizon. It is not an object placed in space. It is space and time arranged into a one-way form, a geometry so deep that every road allowed by physics begins to lean toward darkness. A distant observer watches the fall toward a black hole through a strange kind of delay. A small probe, a cloud of gas, or a fragment of stone may pass through the darkening region outside the horizon, while its last light continues to climb outward, at great distance. The observer does not share the falling object's clock. The observer receives signals only after those signals have travelled through curved space-time, and near the horizon that journey becomes increasingly strained. Each flash of light leaves from a place where gravity is stronger than before. Each flash loses energy as it climbs away. Each one arrives later, stretched farther apart from the last. The result is one of the most famous illusions around black holes. The falling object appears to slow down. Its motion seems to soften into stillness. Its light slides toward red, then deeper into invisible wavelengths. Its image dims until it is not a solid thing at the edge, but a fading memory of something beyond reach. From far away, the horizon seems to hold the object forever, yet this frozen picture is not the object's own reality. It is the story told by escaping light, and that story becomes more delayed, more distorted, and more silent as the crossing approaches. This effect comes from gravitational time dilation, the difference between the rate of clocks in strong gravity and clocks far away. In general relativity, time is not a universal background ticking evenly through the cosmos. It is part of space-time, and it responds to gravity. A clock closer to a massive body runs more slowly, relative to a clock far from that body. Near Earth, this difference is tiny, but real. Near a black hole, it grows without mercy. A clock hovering just above the event horizon, held in place by impossible or nearly impossible force, appears to tick ever more slowly as seen from distant space. A falling object is not hovering, but the light it sends outward must still climb from regions where time is deeply warped. The closer the object is to the horizon when the light is emitted, the more stretched that signal becomes. To the outside observer, moments on the falling object appear increasingly spaced apart. A pulse emitted every heartbeat according to the falling clock arrives with longer and longer gaps. The observer sees time near the horizon losing pace, not because the universe truly pauses there, but because the route between the near-horizon region and far space delays and weakens every message. The reddening is just as important as the slowing. Light carries energy, and the color of light depends on that energy. As a photon escapes from a gravitational field, it gives up energy to climb outward. Its wavelength stretches. Blue light may become red. Red light may become infrared. Eventually the signal may stretch into radio waves, and then into wavelengths so long and faint that detection becomes practically impossible. The falling object does not become red because its surface changes in the ordinary sense. It becomes red to the outside because its light is gravitationally shifted. This redshift joins the time delay to erase the crossing from view. The final signals grow weak, sparse, and stretched. The object is not seen plunging through the horizon in a clean final instant. Instead, it approaches an invisible edge asymptotically, meaning the image gets closer and closer without completing the motion in the outside observer's coordinate time. The last moment becomes endlessly postponed in the mathematical description used far from the black hole, but the postponement belongs to that description. It does not mean that matter piles up forever on the horizon like dust on glass. The outside view is a record of light arriving from increasingly unreachable conditions. The object itself continues along its path. The difference between what the observer sees and what the falling object experiences is central to relativity. There is no single cosmic viewpoint from which all times and all events appear in one absolute order, with one universal rhythm. Observers can disagree about the timing of distant events, especially when gravity is extreme, and still describe the same underlying space-time. The distant observer says the crossing is never seen. The falling object says the horizon is crossed after a finite interval on its own clock. These statements do not cancel each other, because they use different ways of slicing space-time into space and time. The distant observer's coordinates become poorly suited to describing the actual crossing, stretching it toward an unreachable future. Other coordinates, chosen to move with the fall or pass smoothly across the horizon, show no such infinite pause from far away. One description correctly predicts that no signal from the crossing or from inside ever arrives. From the falling path, another permits the object to continue inward. The frozen illusion is therefore not a contradiction. It is a sign that space-time near a black hole refuses to fit ordinary intuition. The idea becomes sharper when the falling object sends regular messages. Far outside the black hole, the messages arrive normally, each separated by the same interval. As the object descends, the arrivals spread apart. The voice of the signal, if translated from light into sound, seems to lower and slow. Information still comes, but each piece comes later than expected and with less energy. Near the horizon, the gaps grow enormous. At the crossing itself, no final announcement reaches the far observer. The message that seems to mark the event is trapped at the boundary in the outside description, unable to arrive at any finite later time. Light itself follows the geometry available to it. At the horizon, the outward direction for light has become a limiting path that never opens into the external future in the usual way. Just inside, even outward-aimed light remains inward bound. The distant observer can therefore build a long history of approach, but never receive the simple report that the object has crossed. The horizon is not witnessed directly by the outside. It is inferred from the silence that follows. This silence leads toward deeper puzzles in black hole physics. If everything seems to freeze near the horizon from outside, then where is the information carried by the falling matter? Does quantum theory require a more delicate accounting than classical relativity provides? In classical general relativity, a distant observer never sees the crossing, while the black hole's mass, spin, and charge can still change as matter falls in. The exterior space-time responds as if the black hole has absorbed what enters, even though the visible image fades before crossing. This is not a simple contradiction, because gravity is not limited to the last photograph of an object. The global structure of space-time includes the fall. The horizon grows and adjusts. The outside can measure the changed black hole, yet the detailed event of entry remains hidden. Knowledge becomes incomplete, because the horizon has removed part of space-time from communication. The image of frozen matter also raises a practical misconception. If many objects fall toward a black hole, the outside observer does not see a bright permanent shell of everything that has ever crossed. The signals fade and redshift so strongly that after enough time they become effectively invisible. The horizon does not become crowded with visible statues. It becomes quiet. New matter falling in can heat the surrounding disk before crossing, but the horizon itself does not shine with the preserved surface of lost things. The last light is stretched thin until it no longer functions as an image. What remains for outside astronomy is not a frozen museum at the edge, but a black region outlined by the motion and radiation of matter nearby. The event horizon keeps its secret not with a wall, but with redshift, delay, and causal separation. In the end, the frozen illusion is one of the gentlest and most unsettling features of a black hole. It shows how an object can be gone and not gone, crossed and not observed crossing, present as a fading signal and absent from all future communication. The contradiction belongs to the viewpoint, not to the falling body. The horizon does not stop time for the traveller. It stops the outside universe from receiving the traveller's later news. The observer far away watches a final approach stretched across an endless mathematical dusk, each signal dimmer than the one before, each interval wider, each colour softened toward invisibility. Then, the story no longer updates. The black hole remains, perhaps a little more massive, perhaps changed by what has entered, but the details have passed behind the one-way boundary. At that quiet edge, light does not end in a flash. It thins into delay. The falling thing does not remain forever in its own experience. It continues beyond the visible record, while the outside observer is left with a vanishing image near a horizon that never quite announces the moment it has concealed. For the falling traveller, The event horizon is not a place announced by impact. There is no floor of darkness rising up to meet the body, no hard shell where motion breaks, no sudden sign written into the local room of space, around a large black hole, especially a supermassive one. The crossing can be strangely quiet. Instruments may still measure the same cabin, the same nearby objects, the same smooth continuation of falling. A watch keeps ticking, a lamp still shines. Nothing nearby needs to declare that the point of no return has passed. This calm is not because the horizon is weak or unreal. It is because the horizon is not a local surface made of stuff. It is a global boundary, defined by whether light sent from an event can ever reach the distant outside universe. The traveller cannot determine its full meaning by touching it, because its meaning depends on the future path of signals across the entire curved space-time in the immediate moment. The horizon may feel like nothing at all, while in the larger map it changes everything. The experience of falling freely is shaped by a principle at the heart of relativity. In a small enough region, a freely falling observer does not feel gravity as a force in the ordinary way. A person falling in an elevator, a stone falling beside a cliff, or a spacecraft drifting along a gravitational path can feel weightless, because everything nearby is falling together. The same idea applies near a black hole, at least over a small region and before tidal forces become overwhelming. Gravity does not press upward through a floor. There is no rocket firing to resist the descent. The traveller follows the straightest available path through curved space-time. From this local perspective, crossing the horizon of a sufficiently large black hole is not like being pulled through a membrane. It is like continuing along a path that already feels natural. The outside universe may describe the same motion as a plunge into a region from which escape is impossible. But the falling frame does not need to register an instant of catastrophe at the boundary. The body does not freeze, the clock does not stop. The horizon slips past as a mathematical truth rather than a physical collision. This difference between local calm and global doom is one of the horizon's deepest lessons. Nature allows a traveller to pass a boundary that cannot be locally marked, while still making that boundary absolute for communication with the outside. An observer far away never receives the final signal of crossing, yet the traveller crosses after a finite interval of personal time. This personal time is called proper time, the time measured by a clock moving along the same path. Proper time remains ordinary for the falling object even when distant coordinates stretch the event toward infinity. The traveller does not wait forever above the horizon. The traveller does not see personal seconds expand into endless suspension. The fall continues. The horizon is crossed. The universe outside is still visible in some directions, but it is no longer reachable by any signal sent after the crossing. A light beam aimed outward from just inside the horizon still travels at light speed locally, yet the space-time through which it moves is shaped so that its future remains inside. The beam does not fail because it slows down. It fails because routes leading to the outside are no longer future-directed. The traveller does not necessarily see the entire future of the universe unfold at the horizon. This common myth grows from mixing the distant observer's time dilation with the falling traveller's experience. A hovering observer held just above the horizon would see outside clocks racing ahead, at least in a coordinate sense, because that observer's own clock is slowed relative to far space. But hovering arbitrarily close to a horizon demands enormous acceleration, and at the horizon itself it becomes impossible for a massive object to remain fixed. A freely falling traveller is different. The light that reaches the traveller comes along the traveller's path like cone, the set of events whose signals can arrive at that moment. Crossing the horizon does not magically open the entire future history of the cosmos. Signals from the far future still need paths that intersect the traveller before the singularity is reached. In many idealized cases, only a finite portion of the outside future can be seen. The traveller may witness the outside universe distorted and shifted, but not all of eternity compressed into a final instant. The horizon hides more than it reveals. It does not grant omniscience, it removes return. The calm crossing also depends strongly on the black hole's size, around a small stellar mass black hole. Tidal forces near the horizon can be severe. Tidal force means the difference in gravity between one part of an object and another. If the feet are much closer to the black hole than the head, they follow a noticeably different gravitational path. The body is stretched along the direction of fall and squeezed sideways. Around a small black hole, this difference can become destructive outside the horizon. In that case, the traveller never experiences a quiet crossing because matter is torn apart before reaching the boundary. Around a supermassive black hole, the horizon lies far from the central region compared with the traveller's size, and the change in gravity across the body can be much smaller at the boundary. The crossing may then be physically survivable in the immediate sense, though not in the final sense. The singularity, or whatever replaces it in a deeper theory, remains ahead in the future. Survival at the horizon is not escape from the black hole. It is only survival at the threshold, once inside. The traveller can still look outward for a time. The event horizon prevents signals from inside from reaching the outside, but it does not instantly prevent outside light from entering. Light from the external universe can continue to fall in after the traveller, in the local frame. Familiar rules still hold nearby. A lamp inside the spacecraft still illuminates the cabin. A signal from a companion who crossed earlier might still be received if the geometry permits the light paths to meet before the singularity. The interior is not simple emptiness. It is a region with future-directed motion, local measurements, and possible signals between events that are also inside. But all such communication belongs to the inward future. Any message sent outward after the crossing remains part of the black hole's hidden interior. The traveller can receive pieces of the universe, but cannot send a piece back. The asymmetry is absolute for the traveller. The most profound change may not be felt as force, but understood as fate. Before the horizon, turning around is difficult but meaningful. A powerful enough rocket, fired early enough, can still alter the path and return to distant space. After the boundary, turning around can still change local motion. The traveller can fire engines, twist orientation, send light, or move within the cabin. Locally, choices remain. Globally, none contains a route back outside. The future is narrowed in a way no engine can widen, because no engine can make matter outrun light, and no signal can exceed its own light cone. The fall inward is no longer one option among several. It is the shared direction of all possible futures. This does not make the moment theatrical. It makes it final. The event horizon, from the falling perspective, is therefore a paradox of silence and consequence. It can pass without a shudder, while erasing every path of return. It can leave nearby physics smooth, while changing the global meaning of every later action. The traveller's clock keeps time. The body may remain intact. The outside stars may still send light inward. Yet after the crossing, no report can climb back to the galaxies beyond the dark boundary. The universe has not ended, but it has divided. Outside, observers inherit only a fading image and a slightly changed black hole. Inside, the traveller continues through space-time toward a future that classical theory says ends at the singularity. The horizon itself remains calm, because it is not a wall. It is more severe than a wall, because it cannot be broken, crossed back, drilled through, or signalled across from within. It is a one-way truth written into geometry. For the falling traveller, the most extraordinary event in the universe may arrive without a sound, without an impact, and without a local mark, as the point of no return passes quietly behind. At every point in space-time there is a boundary of possibility, shaped not by walls but by speed. It is called a light cone, though no physical cone hangs in space, and no object touches its surface. The name is a way of picturing the future and the past allowed by the speed of light. From one event, light can spread outward in all directions, forming the widest possible reach of influence. Anything slower than light must remain inside that widening shape. A drifting stone, a rocket, a burst of gas, a human thought carried by a radio signal, all obey the same limit. The future light cone contains every event that can be reached or affected from the present moment. In ordinary regions of space, the cone seems open and generous. Some futures lead left, some right, some outward, some inward, some back toward home, near a black hole. The cone begins to lean. The range of futures is still there, but the geometry beneath it changes. The closer an event lies to the horizon, the more its cone tilts toward the black hole, until the outward side becomes narrower, steeper, and impossible to use as an escape route. This leaning is not a problem with the light cone itself. Light still moves at light speed locally. The rule that nothing outruns light remains intact. The strangeness comes from the way space-time defines what outward means. Far from a black hole, outward is an accessible direction in space. A light beam pointed away from the mass can increase its distance from the center and reach remote regions. A probe can transmit a signal that spreads into interstellar darkness. The future cone includes paths that escape, closer in. The mass has curved space-time so strongly that the same local rule produces different global result. A beam of light pointed outward may still move outward for a while, but its route is delayed, bent, and red-shifted. A rocket requires more effort to follow a future that avoids the hole. The cone is not closing like a door. It is rotating within the curved geometry, so that more of its interior points toward decreasing radius. At the event horizon, the last outward edge of the future cone lies along the horizon itself. Inside, the entire cone lies within the black hole. The change is absolute because every physical object, every signal, every possible act must travel inside its future light cone. There is no hidden path outside it. A slower than light object cannot choose a direction beyond the cone, and a light beam can only trace the cone's edge. When the cone has tilted inward past the horizon, escape would require a path outside the allowed future, which means faster than light motion. It is not merely difficult, it is outside the structure of causality described by relativity. This is why the horizon is more severe than any strong gravitational field in ordinary language. A planet can be escaped with enough speed. A star can be escaped with a greater speed, even near a dense star. There remains an outward future for light. At a black hole's horizon, the necessary escape speed reaches the one speed that cannot be exceeded. Beneath it, escape is no longer a matter of speed added through space. The future itself has been arranged so that every allowed direction remains inside. A useful way to picture this is to imagine arrows drawn from a falling object, each arrow representing a possible future, far away. Some arrows aim toward the black hole and some away from it. The falling object may choose, within limits, which path to follow. Near the horizon, the arrows crowd inward, a few still barely lean away. At the horizon, the last escape arrow becomes a path that skims the boundary at light speed. A route no massive object can follow and no useful message can ride outward from below. Once inside, all arrows point deeper, even the arrow labelled outward. Even the one traced by a photon fired away from the center still ends at a smaller radius in the future. The labels inherited from outside no longer match the interior reality. What used to be a direction becomes a memory of a direction. The geometry has changed the meaning of choice. This is the heart of the statement that all futures inside a black hole lead toward the singularity. It does not mean every object falls straight downward in the same simple way. An object can still rotate, tumble, shine, fire engines, collide with debris, or exchange signals with nearby companions. Local physics does not disappear at the horizon. Small laboratories still obey the familiar laws of motion in their immediate surroundings, but the larger destination of every future-directed path is fixed within the classical picture. The singularity, or the region where classical theory loses its authority, is not sitting to one side like a dangerous point that might be avoided by steering around it. Inside a non-rotating black hole, it lies ahead in time. The future light cone points toward it because space-time itself has given that direction the status of tomorrow. The falling object may adjust how it arrives, but not whether arrival exists in the classical map. This inward turning also explains why a rescue from outside becomes impossible after a certain point. From a distant perspective, the falling object may appear frozen near the horizon, but that fading image does not mean the object remains available for recovery. A rescue signal or spacecraft must also follow its own light cone. If launched too late, even a beam moving at light speed cannot intersect the falling object before the horizon or before the interior future carries both paths inward. After the rescuer crosses the horizon, the target might become visible again in a limited sense, because signals inside can still meet if their paths are arranged within the same inward falling future. But such a rescue has lost the meaning of escape. The rescuer and the rescued may share information, yet all possible futures remain inside the black hole. The light cone picture also clears away a common misunderstanding about light being pulled back like a thrown stone. In Newtonian thinking, a projectile rises against gravity, slows, stops, and falls. Light near a black hole is not a small ball that tires out and turns around because gravity steals its speed. Locally, light always moves at light speed. What changes is the direction counted as future in the curved spacetime. A photon can be aimed outward from inside the horizon, and in its immediate neighborhood it behaves like light should. Yet that path remains within the horizon, because the horizon is the boundary separating light paths that can reach infinity from those that cannot. The photon does not fail by slowing. It fails because its allowed path still belongs to the inward future. The outside universe is no longer on the map of destinations, in realistic black holes. The geometry becomes more complex, and the simple picture must be handled carefully. Real black holes spin. Their surroundings are full of magnetic fields, plasma, radiation, and in falling matter. Rotation drags space-time around, creating an outer region where staying still relative to distant stars becomes impossible. Yet the essential causal role of the event horizon remains. It is the surface beyond which future-directed light paths cannot reach the distant outside universe. The light cones still tell the story, even when the story bends into more complicated shapes. Their orientation reveals which events can communicate and which are sealed away. Where the cones allow an outward path, the universe can still receive news. Where they do not, the event has become interior. At the horizon, physics discovers that direction is deeper than compass language. The important question is not simply where a path points in a local drawing, but whether that path belongs to the future and where that future can end. Outside the black hole, outward paths exist. At the threshold, they narrow to a limit. Inside, every future descends. This does not require a visible surface, a flash, or a sudden local failure of light. It is a quiet reordering of causality. The horizon is the place where the future light cone stops opening toward the stars and turns wholly toward the hidden interior. Once that has happened, no force, message, or desperate beam can restore the missing direction. The universe outside may continue to shine overhead, its light still able to enter, but the reverse path has been removed from the future. The falling object remains surrounded by local moments, local measurements, and local motion, while the global structure has already chosen the end of every road. At the event horizon, the black hole does not need to pull harder than light. It has made all lights possible. Futures point the wrong way for escape. And in that silent tilt, the boundary becomes complete. A map of a black hole has to do something ordinary maps cannot do. It has to show places that cannot send messages back. It has to show futures that end before they can report themselves. A normal drawing of space and time begins simply enough. One direction on the page can represent time. Another can represent one dimension of space. A beam of light draws a diagonal line, because light moves at the same ultimate speed through every local frame. Slower objects follow steeper paths through time. Their histories are called world lines, thin threads marking the sequence of events they pass through. In flat space-time, such diagrams are already powerful. They show past light cones, future light cones, reachable regions, and forbidden ones. But near a black hole, the diagram becomes difficult. Space-time is curved. Light no longer appears to move along the same simple diagonals if the coordinates are chosen poorly. The lines bend, stretch, and crowd together near the horizon. The drawing begins to hide the very structure it was meant to reveal. The Penrose diagram is a way of rescuing that structure. It is a special map of space-time that keeps light at 45 degrees everywhere on the page, while also squeezing infinite distances and infinite times into a finite picture. This squeezing is called compactification. It does not make the universe smaller. It changes the way the map represents it, placing faraway space, remote future, and distant past at the edges of a single diagram. Light still marks the boundary of possible influence. Anything slower than light remains inside the light cone. The exact distances become distorted. But the question of what can reach what remains visible. That is why the Penrose diagram is so useful for black holes. It does not pretend to show ordinary shapes. It shows possibility, separation, and fate. It turns the horizon from an almost invisible mathematical line into a boundary whose meaning can be seen. For flat space-time, the Penrose diagram resembles a diamond. Its corners and edges gather the infinitely distant past, the infinitely distant future, and faraway space into the borders of the drawing. Light rays travel diagonally from edge to edge, always at the same angle. A particle that drifts through space follows a path inside those diagonal boundaries, never outside them. The whole infinite stage is folded into one finite shape, not by changing physics, but by changing representation. The diagram says, in one glance, which events can communicate. A signal from one event can reach another only if a diagonal light path or slower path connects them in the correct direction. When a non-rotating black hole is placed into such a diagram, the diamond changes. Part of future infinity is cut away and replaced by the event horizon and the black hole interior. The horizon appears as a diagonal boundary, because light itself can trace it, outside the horizon. Some future-directed paths still reach distant infinity. Inside it, future-directed paths end at the singularity. The singularity appears not as a point in space, but as a space-like boundary across the future of the interior. This is one of the diagram's most important lessons. In the simplest black hole, The singularity is not an object sitting at the centre in the ordinary sense. It is drawn as a future edge. Everything inside the horizon has the singularity ahead. Every light cone inside the horizon leans so that its future points toward that boundary. The diagram makes the phrase "no escape" less like a slogan and more like a visible fact. A falling object can be drawn as a world line that begins in the outside universe, crosses the diagonal horizon, and ends at the singularity. A light signal emitted by that object before crossing may still escape if it leaves early enough and at the right angle. A signal emitted too late may approach the horizon but fail to reach faraway observers. A signal emitted after crossing remains inside forever. On the Penrose diagram, these differences become clear without needing dramatic language. The diagonal paths either reach future infinity or they do not. The event horizon is the dividing line between those outcomes. The falling object does not freeze on its own world line. It crosses the horizon smoothly. The outside observer's inability to see that crossing is represented by the fact that no future-directed light path from the crossing reaches the observer's region at distant infinity. The map separates experience from observability. It shows why both descriptions can be part of one space-time. The frozen image belongs to the pattern of signals arriving outside, not to the traveller's local passage. The Penrose diagram also helps explain why the horizon is not merely a place where light struggles. Light paths are the edges of causal influence. If a diagonal line from an interior event cannot reach the outer region, then nothing else can. A rocket, a stone, a radio message, and a cloud of plasma all move within or along the same causal limits. The diagram removes the temptation to imagine a stronger engine finding a clever route. There is no route outside the light cone, and the cones inside the horizon all point toward the singularity. To escape from inside, a path would have to slant outside the diagonal boundary allowed for light. That would mean faster than light influence. In relativity, that is not a hidden technology waiting to be built, but a violation of the structure that defines cause and effect. The black hole interior is therefore not a prison with locked doors. It is a region where the map contains no outward future. There is another subtle gift in this map. It shows that the event horizon is not defined by local violence. A world line can cross the horizon without any kink, break, or sudden mark. The line continues. The light cones remain locally normal in their own small neighbourhoods. What changes is their relation to the outer edges of the diagram. Before crossing, some future signals can still reach the far universe. After crossing, none can. The difference is global. It depends on the whole causal layout, not on a local surface that a falling observer must feel. In this way, the Penrose diagram gives a calm shape to one of the hardest ideas in black hole physics. A boundary can be physically real because it changes communication forever, even if nothing local announces it at the moment of passage. The simplest diagram can be extended mathematically into stranger territory. The full eternal Schwarzschild solution contains a second exterior region and a white hole region. The second exterior is sometimes described as another universe, connected in the mathematics by an Einstein-Rosen bridge. The white hole is the time reverse of a black hole, a region from which things emerge but into which nothing can enter. These features are not usually treated as realistic objects formed by collapsing stars. They arise from an ideal solution that does not include the history of stellar collapse. Still, their presence is useful. They show how much richer the mathematics of horizons can become, and how carefully the map must be interpreted. Real black holes are expected to be born from collapse, to spin, to be surrounded by matter, and to evolve. A rotating black hole has a more complicated causal structure, with regions where space-time itself is dragged around, and inner horizons appear in the idealized solution. Penrose diagrams for such objects can unfold into repeating patterns that suggest further interiors and possible passages. Though many of these features may be unstable once realistic disturbances are included, the value of the diagram is not that it turns speculation into certainty. Its value is that it keeps the speculation honest. It shows which paths are allowed by a chosen model and which are not. It gives the mystery a geometry. At the event horizon, that geometry is severe and simple. Outside, diagonal lines of light may still reach the distant future. Inside, they cannot. The Penrose diagram compresses forever into a finite page and reveals that the black hole's darkness is not merely a failure of sight. It is a causal boundary drawn through space-time. The horizon is where the outside universe loses access to a set of events, and the diagram shows that loss without spectacle. A falling world line crosses a slanted edge. A last escaping ray peels away. Later, rays remain trapped. Above the interior waits the singular boundary where classical theory runs out. Around the page, infinities sit quietly at the edges, reminding physics that the question is not only what happens, but who can ever know that it happened. In that single compressed map, the event horizon becomes less like a dark surface and more like the line where stories separate, where one future remains visible to the cosmos and another turns inward beyond all return. One of the most persistent myths about the event horizon says that a falling traveller sees the whole future of the universe before crossing, as though the black hole becomes a final theatre where cosmic history races to its end. The last light of the far future pours down into a single instant. The image is powerful, but it is not what the simplest physics says. It comes from a real effect, then stretches that effect beyond its proper frame. Time near a black hole does behave strangely when compared with time far away. A clock held just above the horizon appears, from distant space, to tick more and more slowly. Signals climbing out arrive increasingly delayed and redshifted. From that distant viewpoint, a falling object seems to approach the horizon without ever completing the crossing, but reversing that view too casually creates confusion. If the outside sees the falling clock slow, it may seem that the falling traveller must see the outside universe speed up without limit. The truth is more careful. What any observer sees is not the universe in some universal present, but the light that actually reaches that observer along possible paths through space-time. The event horizon does not open a window onto all future events. It limits which events can communicate at all. The key idea is the past-light cone. For any moment on the traveller's path, the past-light cone contains all events that can send light to that moment. It is a causal boundary. Light from a star, a galaxy, or a distant clock must travel along a path that intersects the falling traveller before that traveller reaches later interior regions. If no such path exists, the event cannot be seen. Even outside the black hole, the traveller never sees the universe as it is everywhere at once. Vision is always delayed by distance. The sun is seen as it was minutes ago. Distant galaxies are seen as they were millions or billions of years ago, near a black hole. These delays tangle with gravitational time dilation and curvature, but the rule remains: only arriving light can be observed. The far future of the universe is not automatically delivered to the horizon. It must send signals early enough, along paths that can catch the falling observer before the interior future ends at the singularity in the classical picture. A freely falling traveller has only a finite amount of proper time after crossing the horizon of a non-rotating black hole before reaching that final boundary. For a stellar mass black hole, this time can be brief. For a supermassive black hole, it can be longer, but still finite. During that interval, light from the outside may continue to fall inward and reach the traveller. Some events that occur outside after the traveller crosses can be visible, depending on their location, timing, and the black hole geometry. But this is not the same as seeing all of cosmic history. There is no guarantee that signals from arbitrarily late times have enough opportunity to arrive. The traveller's world line ends, in the classical map, before infinite external time can be received in an ordinary observational sense. The horizon is a boundary of escape, not a machine that compresses eternity into sight. The misconception often grows stronger when the observer is imagined as hovering just above the horizon rather than falling freely. Hovering means resisting the natural fall. A rocket must fire continuously to remain at a fixed radius. The closer the hovering position lies to the horizon, the greater the required acceleration becomes. In the ideal mathematical limit at the horizon, hovering is impossible for any massive object. A hovering observer very near the horizon would indeed experience an extreme form of time comparison with distant clocks. The outside universe could appear sped up, and incoming radiation could be shifted in complicated ways. But that is not the same experience as freefall. The hovering observer is not calmly crossing the boundary. That observer is violently resisting the geometry, maintaining an unnatural path. The falling traveller follows a different world line, and therefore has a different past-like cone. The view of the universe is governed by that path, not by a simple slogan about time stopping. There is also a question of direction. Near and inside the horizon, the outside universe doesn't necessarily fill the whole sky in a normal way. Light paths are bent by the black hole's curvature. Images can be distorted, concentrated, shifted, and wrapped around the dark region. For an infalling observer, light from the outside may appear compressed into certain directions, while the black hole's interior future dominates the path ahead. The visual appearance depends on mass, spin, motion, and environment. An empty, ideal black hole gives clean geometry, but real black holes may be surrounded by radiation, gas, magnetic fields, and bright accretion disks. Still, the essential point remains gentle and firm. Seeing strange distortions is not seeing every future. The horizon changes access, but it does not grant universal knowledge. In some idealized coordinates, the external universe's time can appear to run far ahead as the horizon is approached. Coordinates are ways of labeling events, and around a black hole some labels become misleading if treated as direct experiences. A distant time coordinate stretches the crossing toward an infinite future. In that same coordinate language, the falling traveller may seem to approach a place where outside time has advanced immensely. Yet physical observation is local and causal. It is built from photons, particles, clocks, and measurements along a path. A coordinate that assigns very large external times near the horizon does not automatically mean the observer sees all those times. The Penrose diagram clarifies this by drawing not coordinate impressions, but causal connections. A past-like cone intersects only part of the outside universe. It does not swallow the entire upper edge of future infinity at the crossing. The map shows that the traveller's accessible view has boundaries. A myth dissolves when the light paths are traced. Black holes are already mysterious enough without impossible powers. Their real physics is subtler than the fantasy. The outside observer never sees the crossing completed, while the traveller crosses in finite proper time. Signals from the traveller become delayed and redshifted, while signals from the outside can continue inward. These facts together create a symmetry, not omniscience. The horizon lets information fall in more easily than it lets information out. It is a one-way causal surface. For the traveller, that one-way nature means the universe outside may still be partially visible, perhaps distorted, perhaps brightened, perhaps shifted in energy, but no later message can be returned. The traveller may receive, but not answer. The black hole allows a final inward listening, not a final complete vision. Knowledge comes in fragments along allowed paths, while the larger future of the cosmos continues beyond communication. The deepest reason is that the event horizon is not a place where time becomes infinite for everyone. It is a boundary whose meaning depends on causal relation. The distant observer's description, the hovering observer's description, and the falling observer's description each emphasize different slices through the same space-time. None is permitted to ignore how light actually travels. A falling clock does not stop at the horizon. A distant clock does not become magically visible through all future ages. The universe does not arrange its whole remaining story into a last private display. Instead, the crossing remains quiet, constrained, and incomplete. It offers no final answer about the far future, only a sharper demonstration that observation is limited by geometry. The black hole denies return and hides events beyond the boundary. It does not turn the traveller into an all-seeing witness. The event horizon therefore carries a stranger kind of humility. It is not a gateway to cosmic spoilers. It is a place where even the idea of seeing must obey causality. The outside universe may continue for trillions of years, or far longer, with stars fading, remnants cooling, and galaxies slipping beyond each other's horizons. The falling traveller does not gain possession of that whole story. Only the light that arrives along the narrowing geometry can be known, and only for the finite time remaining inside the classical black hole. Beyond that, current theory points toward a singular boundary where its own predictions lose clarity. The horizon remains what it has always been, not a screen showing eternity, but a quiet divider of possible communication. It allows the outside to fall inward in glimpses, while preventing the inside from speaking back. At its edge, the future is not revealed in full. It is divided, hidden, and carried onward through paths that no single observer can command. Around a black hole, the boundary that cannot be escaped is not always the boundary that destroys. This is one quiet surprise inside the event horizon. The horizon marks the place where all future-directed paths remain inside the black hole. But danger to an object comes from something more local and more physical. It comes from the difference in gravity across distance. A falling body is not a single mathematical point. It has length, width, and depth. One side can be closer to the black hole than another. If the closer side is pulled along a noticeably different path from the farther side, the object is stretched. If the sideways directions are squeezed at the same time, matter begins to narrow as it lengthens. This tidal effect is sometimes called spaghettification, a strange informal word for a precise gravitational process. The name can sound theatrical, but the physics is simple. Gravity is stronger closer to the mass. And around compact objects it can change sharply over small distances. That change, not the horizon itself, decides whether a falling object remains intact at the threshold or is transformed before it ever reaches it. Tidal forces are familiar in gentler form. The moon pulls more strongly on the side of Earth facing it than on the far side, and this difference helps raise ocean tides. The sun does the same, though its effect depends on distance as well as mass. On Earth, the difference is small enough to create a rhythm of seas, not a tearing of rock. Near a black hole, the same principle can become immense because the source of gravity is packed into a far smaller region. The strength of gravity matters, but the rate at which it changes with distance matters even more. A person freely falling near Earth feels nearly weightless, because every part of the body follows almost the same path. But if the difference between head and feet becomes large enough, freefall no longer feels uniform. Each part is being directed along a slightly different geodesic, The body is not being crushed by a surface, it is being separated by the geometry of nearby paths. The smaller the black hole, the more severe this can be near the horizon. This seems backward at first, because supermassive black holes contain far more mass, yet the radius of the event horizon grows in proportion to mass. A black hole with millions or billions of solar masses has an enormous horizon, and at that large distance from the centre, the change in gravity across a small object can be surprisingly mild. A stellar mass black hole has a much smaller horizon, so the same crossing occurs much closer to the central region where curvature changes rapidly. The result is that a small black hole can have devastating tidal forces at or outside its horizon, while a supermassive black hole can allow a calm passage through the horizon in the immediate local sense. The larger black hole is not safer in any final way. It only moves the strongest tidal danger deeper inside. The horizon of a supermassive black hole can be crossed before the destructive gradient becomes extreme. This distinction separates two ideas often blended together. Escape is a causal question. It asks whether a future-directed path can lead outward to the larger universe. Tidal destruction is a local curvature question. It asks how differently nearby parts of the same object are made to fall. The event horizon answers the first question. The strength of curvature across the object answers the second. A small black hole may answer both at nearly the same place, making the horizon region physically violent. A large black hole may separate them, so that the point of no return is quiet while the fatal tidal region waits farther ahead. In the language of relativity, the falling object can cross the horizon smoothly because space-time is locally well behaved there. Nothing at that exact surface has to become infinite. The singularity lies in the future of the interior, and the curvature grows as the path moves inward. The horizon is the start of no return, not necessarily the start of immediate ruin. The scale difference can be striking. If a massive star collapses into a black hole only a few times the mass of the Sun, the event horizon is small on astronomical scales. The central curvature is close by. Tidal forces outside the horizon may become so intense that an ordinary object cannot remain whole long enough to cross. If the black hole has the mass of millions of suns, like the one at the centre of the Milky Way, the horizon is vast compared with human-sized objects, planets, and many ordinary spacecraft scales. At the crossing, the difference in gravitational pull across a small body may be modest. The object may pass through the horizon with no local alarm, even though every possible future now lies inside. If the black hole has billions of solar masses, the effect at the horizon can be gentler still. The darkness may be larger than an entire planetary system, while the local tidal gradient at its edge is less dramatic than intuition expects. This does not make the interior peaceful forever. It only delays the moment when curvature becomes unavoidable in the body itself. Tidal forces also shape the visible environments around black holes. A star that passes too close may be distorted by the gradient of gravity before it crosses the horizon. Its gas can be pulled into long streams, heated, and spread into an accretion flow that shines as it falls. This kind of tidal disruption can release extraordinary energy outside the horizon, where light still has outward paths. The black hole remains dark, but its surroundings flare because matter is being forced through changing gravitational routes before disappearing. In such events, the horizon is not the glowing source. The radiation comes from the last visible struggle of matter outside the boundary, where collisions, compression, and magnetic fields convert orbital motion into heat and light. The silence belongs to the inside. The same principle applies to smaller pieces of matter. Dust grains, rocks, gas clouds, and compact stellar remnants all respond differently depending on their size, strength, and path. A diffuse gas cloud can be stretched and stirred long before compact matter would fail. A neutron star or white dwarf can resist deformation longer than ordinary material, because its internal pressure and density are extreme. Yet the tidal field near a black hole can overcome even very strong structures if the encounter is close enough. Matter approaching a black hole is sorted by orbit, angular momentum, magnetic environment, and tidal gradient. Some material escapes after a close swing, some forms a disk, some plunges inward, some is stretched into streams before part of it vanishes. The event horizon is the final causal boundary within this larger choreography, but much of the visible drama happens outside it. For the falling traveller, the approach to tidal danger would not feel like ordinary weight in one direction. In free fall, there is no floor pushing upward, no single downward pull felt through the body as on a planet. Instead, there is relative acceleration between neighbouring parts. Objects floating nearby drift apart along the radial direction and converge in sideways directions. At first, the effect may be too small to notice. Deeper inward, it grows. Instruments would measure increasing differences between points that were once nearly at rest relative to each other. The local laboratory begins to reveal that space-time is not merely carrying everything together. It is bending nearby paths away from shared motion. The horizon may already be behind, but only now does the body learn through local physics that the interior is not endless calm. Geometry that seemed smooth at the boundary becomes increasingly severe. General relativity predicts a singularity for the simplest black holes, a place where curvature grows without bound, and known equations lose their power. Tidal forces increase on the way toward that boundary, but what truly happens at the deepest end is not known. Quantum gravity may replace the singularity with something else, or it may reveal that space-time itself changes character under such conditions. The safe statement is that classical theory expects tidal effects to become overwhelming before the end, while the exact final description remains unfinished. The event horizon therefore sits at the beginning of a hidden sequence. It does not have to destroy, but it commits every future to a region where transformation or unknown new physics lies ahead. Around a small black hole, the warning may arrive before the threshold. Around a giant one, the threshold may pass in quiet. With the strongest tides waiting deeper in the dark, the difference is not mercy, it is scale. Black holes teach that size changes fate, and that the most absolute boundary may be crossed long before its full force is felt. Inside the event horizon, the black hole is often described as a one-way river, but even that image has to be handled with care. A river flows through space, and a strong swimmer may imagine fighting the current. The interior of a black hole is more severe. It is not only that space is flowing inward, or that gravity is dragging matter too strongly. The deeper statement is that the direction toward the center has become tied to the future itself. Outside the horizon, a traveler can point a rocket inward or outward, a stone can fall, a beam of light can escape, a satellite can orbit, and the distance from the black hole remains a spatial question. Inside the horizon, the classical geometry changes the meaning of that distance. Decreasing radius is no longer merely one direction among others, it becomes the direction in which future-directed motion must proceed. The singularity is not waiting somewhere like a stone at the bottom of a well. In the simplest non-rotating black hole, it lies ahead as a future boundary, as unavoidable as the next moment is outside. This is why the phrase space behaves like time carries a real, though subtle, truth. In ordinary life, movement through space is optional. A person can walk north or south, turn around, stop, return, or choose another path. Movement through time is different. No ordinary action lets a clock reverse its aging or step away from tomorrow. Time is the direction in which change proceeds, the dimension with a one-way character built into experience. Inside a black hole, the radial direction toward the singularity gains a similar one-way quality. The falling traveller can still move locally. A hand can be raised. A lamp can shine. A device can send a signal across a cabin. A rocket can fire and alter the path. But none of those actions changes the larger fact that all allowed futures remain inside and approach the singular boundary. Turning around can change orientation, but it cannot make the external universe become a reachable future again. The lost possibility is not a failure of effort, it is a feature of the geometry. This interior does not need to feel instantly alien in every local measurement. The equivalence principle still protects small enough regions from revealing gravity as a simple force. A freely falling laboratory can remain weightless for a time. Nearby objects can drift alongside one another. Local beams of light still travel through the room at light speed. The equations of physics do not stop at the horizon. What changes is the global arrangement of where those local actions can lead. A sealed spacecraft may find nothing at first that announces an absolute boundary behind it. Yet if the experiment tries to send a message outward to the distant stars, the larger space-time refuses. The message may move outward in a local sense, but its world line still belongs to the interior. It may meet another infalling object, or curve along a path deeper inside, but it cannot reach future infinity. The universe outside has become part of the past of the black hole interior, still able to send light in, but not part of the interior's reachable future. The one-way nature of the interior can be seen through the light cones introduced earlier. Outside the horizon, the future light cone has room for escape. At the horizon, its outward edge lies along the boundary. Inside, the whole cone points towards smaller radius. That does not mean every cone points in a visually downward direction on every possible drawing. It means every future-directed path that respects the speed of light remains trapped within the black hole and ends, in the classical model, at the singularity. Even a photon fired outward traces a route that fails to increase its radius enough to escape. A massive object has even less freedom, because it must stay inside the light cone rather than on its edge. The interior is therefore not a place where escape is blocked by an obstacle. It is a place where escape is absent from the catalogue of futures. No amount of ordinary acceleration can change that. Acceleration chooses a different allowed path. It does not redraw the paths. The river image still has value if it is softened. Outside the horizon, space-time can be pictured as flowing inward more and more rapidly, while light and matter attempt their paths within it. Far from the black hole, the flow is gentle enough that outward motion can overcome it. Closer in, outward motion becomes harder. At the horizon, the inward flow reaches the speed of light in one useful picture. Inside, it exceeds that speed relative to distant coordinates, so even light moving outward is carried inward overall. This picture is not the full truth, because space-time is not a substance rushing through a channel, but it captures the loss of return. A fish in a river may swim through water. A traveller in a black hole moves through space-time whose causal structure is tipped inward. The current is not merely strong. It defines what counts as downstream for the future. Once inside, there can still be a sky of sorts, but it is a strange one. Light from outside the black hole can continue to enter. The exterior universe is not erased from view at the horizon. Signals that cross inward after the traveller may catch up along certain paths. Light from stars, gas, or an accretion disk may be bent, shifted, concentrated, or distorted. The traveller may receive information from events outside that occur after the crossing, depending on the geometry and timing. Yet this visible outside is no longer a destination, It is more like light falling into the same hidden future. The traveller can observe fragments arriving from above, but cannot return a reply to the places that sent them. Communication has become asymmetric. The outside can still contribute signals to the interior. The interior cannot answer. The black hole has turned observation into a one-way inheritance. In the simplest classical case, the time remaining inside depends on the mass of the black hole and on the path taken, but it is finite. Larger black holes give longer intervals between horizon and singularity, while smaller ones give shorter intervals and stronger tidal forces sooner. For a supermassive black hole, the passage from horizon to deeper danger may allow a brief continuation of ordinary processes. Clocks tick, chemical reactions proceed, memories form, instruments record, but every record remains trapped. The interior can contain events, sequences, and experiences, yet none become part of the outside universe's later knowledge through direct signals. This is one of the black hole's quiet cruelties from the standpoint of information. It does not prevent things from happening. It prevents their reports from leaving. The hidden region is not empty of history. It is empty of exportable history. The approach to the singularity changes the calm. As radius decreases, tidal forces grow in the classical description. Objects stretch along the radial direction and compress across the other directions. The local laboratory can no longer ignore curvature. Instruments that once drifted together begin to separate or converge in patterns that reveal the geometry's violence. The one-way river narrows into a region where space-time curvature itself becomes the dominant fact. The singularity, as general relativity describes it, is not just a dense object but a breakdown of the classical space-time description. Curvature becomes infinite. Predictive paths end. The theory indicates its own limit. A deeper quantum theory of gravity may replace this end with some other structure, perhaps one without an actual infinity, but no confirmed answer currently completes the picture. The interior therefore leads from smooth geometry at the horizon toward an unknown where known geometry thins out. Real astrophysical black holes almost certainly spin, because stars rotate and in falling matter carries angular momentum. Rotation drags space-time around and changes the hidden structure, giving ideal mathematical models inner horizons and startling causal possibilities. Some diagrams suggest passages into further regions, but such features may be unstable under realistic disturbance. Still, the outer event horizon keeps its central meaning. Once crossed inward, no signal returns to distant space. Inside the event horizon, the black hole is not simply a darker place. It is a different causal world. The traveller still has local moments, choices, and measurements, but all of them unfold within a future that narrows toward the hidden end. Outside, time carries every object forward. Inside, the radial fall takes on that same inevitability. The singularity or its unknown replacement lies not as a place to visit, but as the direction in which the future points. The event horizon has already removed the stars as reachable destinations. It has left only inward continuation, a quiet descent through geometry where space has borrowed the certainty of time, and every road allowed by physics flows deeper into the dark. At the heart of the simplest black hole, the map of general relativity ends in a place where the theory speaks clearly and falls silent. This place is called the singularity, but the word can mislead. It is not a small solid bead hidden inside the darkness, not a crushed star with a surface, not a point that could be approached with ordinary instruments and measured like a planet. In the classical equations, the singularity is where space-time curvature becomes infinite, and where the paths of falling matter and light end. It is a boundary of prediction, a sign that the mathematical description has reached a limit. General relativity says that once matter has crossed the event horizon of a non-rotating black hole, the inward future leads toward this end. It gives a clean and severe result, but that result may not be the final physical truth. Infinite quantities in physics often signal that a theory is being used beyond the range where nature permits it to remain complete. The singularity is therefore both a prediction and a warning. It is what the classical theory points toward, and also the place where a deeper theory is expected to be needed. The route to this uncertainty begins with collapse. A massive star supports itself for most of its life by balancing inward gravity with outward pressure from heat, radiation, and nuclear reactions. When the fuel that maintains this balance is exhausted, the core can contract. If the remaining core is not massive enough, other forms of pressure can halt the collapse, leaving a white dwarf or a neutron star. If enough mass remains, known pressures fail. Gravity keeps tightening the geometry until an event horizon forms. Once the horizon exists, the interior is hidden from outside observers, but the classical equations can still describe the continuing fall. They show no stable surface waiting within the horizon. They do not allow matter to settle peacefully at some inner shell. In the non-rotating ideal case, the radial direction toward the center behaves like a future direction, and that future terminates at the singularity. This is not because matter chooses the shortest path downward. It is because the structure of space-time permits no other final destination. As the fall continues inward, tidal forces grow. Nearby paths through space-time that once remained almost parallel begin to diverge and converge more sharply. Extended objects are stretched along one direction and squeezed along others. For a small black hole, this process becomes overwhelming quickly. For a supermassive black hole, the early interior may be milder, but the classical trend remains. Curvature increases as the singular boundary approaches. At the deepest level, general relativity predicts that the curvature does not merely become large, it becomes unbounded. The density associated with the collapsed matter is often described as infinite, though that phrase belongs to the mathematical model rather than to a confirmed physical object. No experiment can look out from that region, no signal can return. The prediction is sealed behind the horizon, and the theory itself loses its ability to continue world lines beyond the end. The singularity is not just a strange object inside a black hole. It is the point where the usual idea of space-time as a smooth arena ceases to function. This is where quantum physics enters the mystery. General relativity describes gravity and the large-scale shape of space-time with extraordinary success. Quantum theory describes particles, fields, and the small-scale behavior of matter with extraordinary success. Both have been tested again and again in their own domains, but near a black hole singularity, both domains collide. The curvature is gravitational and extreme. The scales may become so small that quantum effects can no longer be ignored. A complete description should somehow include gravity as part of quantum reality, or reveal a deeper framework from which both classical spacetime and quantum fields emerge. Such a theory is often called quantum gravity. It remains unfinished. Several approaches exist, and each offers clues, but none has yet provided a confirmed, complete description of what replaces the classical singularity inside an astrophysical black hole. The event horizon hides the answer from direct observation, making the problem even more difficult. The central question is not simply what matter becomes when crushed. It is what space-time itself becomes when compression goes beyond the smooth geometry that relativity assumes. In ordinary physics, space and time are the stage on which fields change and particles move. In general relativity, the stage is dynamic, bending and evolving with matter and energy. Near the singularity, The stage may no longer behave like a continuous surface. It may fluctuate, fragment, or be replaced by a structure that has no meaning in ordinary language. Some ideas suggest that the singularity could be resolved into a finite but extreme region. Some imagine a bounce into another phase of space-time. Some propose that information is stored in ways connected to the horizon rather than the central end. These remain cautious possibilities, not settled facts. The safe conclusion is more modest and more profound. The equations that have guided physics so well predict their own breakdown under the conditions they create. The black hole is therefore not only an object in the universe, it is a laboratory for the limits of theory. Rotation makes the question even more intricate. Real black holes are expected to spin, because the stars that collapse into them spin, and because matter falling in carries angular momentum. A rotating black hole is described by a more complex solution than the non-rotating Schwarzschild case. Its interior contains inner horizons in the ideal mathematical model, and some versions suggest paths into extended structures beyond the familiar exterior. Yet these possibilities cannot be treated as reliable travel routes or confirmed cosmic passages. Inner horizons may be unstable. Tiny disturbances, infalling radiation, and realistic matter can be amplified in ways that radically change the interior. The elegant diagram may not survive the roughness of the real universe. Still, rotation matters because it shows that the singularity problem is not a single solved shape. The event horizon is robust, but what lies deeper may depend on details that classical theory only partly controls. There is also a difference between a singularity as a mathematical feature and a singularity as a physical claim. A mathematical singularity means the equations produce values that stop making sense, such as infinite curvature or incomplete paths. A physical singularity would mean nature actually contains such an end. Physics has often learned to distrust infinities. An infinity can mark missing structure. It can mean that a more careful theory must replace the old one at shorter distances or higher energies. The black hole singularity may be the same kind of warning, yet it cannot be dismissed casually, because it arises from one of the most successful theories ever built. General relativity drives there with mathematical force once collapse passes a threshold. That is why the problem remains so deep. The theory is trusted, and the prediction is unacceptable as a complete ending. From outside, the singularity is never observed directly. The event horizon prevents any report from the interior. Astronomy can measure the mass and spin of black holes, watch matter orbit and flare outside them, detect gravitational waves from mergers, and image the shadow cast by light bending near the horizon. These observations confirm black holes as real astrophysical objects very close to what relativity predicts. They do not reveal the central end. The singularity is inferred through theory, not photographed. It is approached by equations rather than by sight. This distance between evidence and interior truth gives black holes their enduring power. They are among the best confirmed predictions of relativity, and at the same time they contain a region where relativity points beyond itself. The known and the unknown are not separate here. The event horizon is the outer seal. The singularity is the inner question. The most careful answer to what happens at the centre is therefore unfinished. Classical general relativity predicts a singular boundary where curvature becomes infinite and all inward futures end. Quantum reasoning suggests that this cannot be the complete physical story, but does not yet supply one confirmed replacement. The black hole holds these truths together without resolving them. At the horizon, the outside universe loses contact. Deeper inside, tidal forces grow and the classical path narrows. Near the end, space-time itself becomes the subject of uncertainty. The singularity is not a spectacle waiting to be seen. It is a silent mark at the edge of knowledge, a place where a powerful theory reaches its own shadow. Somewhere beyond the smooth language of relativity, nature may have a different grammar. Until that grammar is known, the center of the black hole remains less a destination than a question, carried inward by every falling path, hidden behind the horizon, where the future of matter and the future of physics become the same unresolved dark. The event horizon is not only a boundary of escape, it is also a boundary where the rules of knowledge become difficult to keep together. In classical general relativity, the black hole is simple from the outside, after matter falls in and the surrounding disturbances settle. The exterior can be described by a few properties: mass, spin, and electric charge. The detailed story of what formed the black hole seems to vanish from the external description. A star, a cloud, a planet, a library, or a beam of radiation may fall through the horizon, and the distant universe can measure only the black hole's gravity and rotation. The individual arrangement of atoms, fields, and histories becomes hidden. For classical physics, this concealment is not necessarily a crisis. The information is behind the horizon, unreachable, but not obviously destroyed. It remains part of the full space-time, sealed away from outside communication. But quantum physics is less comfortable with such quiet disappearance. In quantum theory, information about the state of a system is not supposed to be erased from the universe. It may become scrambled beyond practical recovery, but the underlying evolution is expected to preserve it. Black holes place this expectation against the one-way darkness of the horizon. The tension sharpens with Hawking radiation. In the 1970s, Stephen Hawking showed that when quantum fields are considered near the horizon of a black hole, the black hole should not remain perfectly black forever. It should emit faint thermal radiation, slowly losing energy and mass. The common picture speaks of particle pairs near the horizon, with one escaping and the other falling inward, but that image is only a rough guide. The deeper idea is that the vacuum of quantum fields is affected by curved space-time and by the existence of a horizon. What looks empty is not empty in a simple classical sense. Quantum fields have fluctuations, and the distinction between particles and no particles can depend on the observer and on the geometry. The horizon changes how modes of the field are related between the far past and the far future, producing radiation seen at a distance. For a large astrophysical black hole, this radiation is incredibly cold and faint, drowned out by the cosmic environment around it. Yet over immense times, if nothing new falls in, the black hole loses mass. The smaller it becomes, the hotter it gets, and the faster the evaporation proceeds. Hawking radiation changes the meaning of the horizon. A classical black hole can hide information indefinitely, because it can last forever in the idealized model. A quantum black hole appears to evaporate. If it disappears completely, then the question becomes unavoidable. What happens to the information carried by everything that fell in if the radiation is purely thermal, meaning it carries only a featureless pattern determined by temperature and not by the detailed contents of the black hole? Then the information seems lost. A black hole could form from many different initial states and evaporate into the same kind of radiation. That would violate the usual quantum rule that different beginnings remain distinguishable in principle, even if no practical observer can reconstruct them. This is the black hole information paradox. It is not merely a puzzle about missing records. It is a conflict between the smooth causal horizon of general relativity and the information-preserving evolution of quantum mechanics. The horizon sits directly between them. It is where the outside loses access, where the interior keeps the fallen details, and where quantum fields appear to allow the black hole to leak away. Several possibilities have been considered, each difficult in its own way. information might truly be destroyed, forcing quantum theory to change at its foundations. But that option is hard to accept because quantum theory has been so successful, and because information loss can lead to deeper inconsistencies. Information might escape in Hawking radiation after all, hidden in subtle correlations too delicate to appear in the simplest calculation. This option preserves quantum theory, but it asks the horizon to behave less innocently than it appears in classical relativity. Something about the radiation must know, in a highly scrambled way, what entered the black hole. Information might be stored at or near the horizon, connected to the idea that the surface area of a black hole measures its entropy, a count of hidden microscopic states. This has led to the holographic principle, the possibility that information in a volume of space can be represented on a boundary. The idea is strange, but black holes make it difficult to avoid. Their entropy grows with horizon area, not with interior volume, suggesting that horizons may count reality differently from ordinary matter. Entropy gives the mystery a thermodynamic form. In everyday physics, entropy is linked to the number of microscopic arrangements that can produce the same large-scale appearance. A black hole looks simple from outside, but it carries enormous entropy. The area of its event horizon behaves as though it measures the number of ways the black hole can be internally arranged, while presenting the same exterior mass, spin, and charge. This connection between gravity, quantum theory, and thermodynamics is one of the strongest clues that the event horizon is not just a passive boundary. It may be where deep principles meet. Temperature, entropy, radiation, and geometry all become part of the same object. The horizon turns a black hole from a final trap into a system with a temperature, a lifetime, and a hidden accounting problem. There are more dramatic proposals, though they remain unsettled. Some ideas suggest that an infalling observer might encounter a firewall, an energetic breakdown at the horizon caused by the demands of quantum information. This would violate the calm crossing predicted by general relativity for a large black hole. Other ideas argue that no such violent surface exists, and that information escapes through subtler effects or through a more complete understanding of space-time. Some approaches look to quantum gravity, where space-time itself may not be fundamental, and where the distinction between inside and outside could be emergent rather than absolute. None of these possibilities should be treated as settled. The paradox remains powerful because every clear answer seems to demand a sacrifice. Either the horizon is less smooth than relativity says, or information behaves differently than quantum theory says, or space-time is not built the way ordinary geometry suggests. The problem grows over a black hole's lifetime. At first, a large black hole emits extremely little Hawking radiation. It can absorb far more energy from its surroundings than it loses, but in an empty future, after stars fade and background radiation cools, evaporation becomes the long final process. The black hole shrinks slowly for ages beyond ordinary imagination. Its temperature rises as its mass falls. Near the end, the classical picture becomes unreliable, because the black hole becomes small enough that quantum gravity should matter strongly. The final stage is unknown. It may end in a burst, a remnant, a transition, or something not yet described by current language. The information question follows the entire path. If information comes out, it may emerge only after being scrambled across the radiation in an almost unreachable pattern. If it remains, something must hold it when the black hole is gone. If it is destroyed, a central expectation of quantum physics fails. The event horizon, quiet at the crossing, becomes a long-term crisis for theory, for stellar and supermassive black holes in the universe. Hawking radiation is far too weak to see directly. Their surroundings are brighter, warmer, and noisier. The radiation is important not because it currently makes most black holes visible, but because it reveals that horizons have quantum consequences. A perfectly dark one-way boundary cannot remain perfectly simple once quantum fields are included. The vacuum notices the horizon. The black hole has a temperature. The hidden interior becomes part of an accounting problem written across unimaginable time. This is the strange gentleness of the information paradox. It begins with faint radiation, almost nothing, a whisper below the brightness of the cosmos. Yet within that whisper lies one of the hardest questions in physics. The event horizon first appears as the place where escape ends. Then it becomes the place where observation ends, with Hawking radiation. It also becomes the place where two great theories press against each other. The black hole may hide what falls through, but if it slowly evaporates, hiding is not enough. The universe must decide, or reveal through deeper law, whether information is lost, stored, returned, or transformed into something not yet understood. The answer remains suspended between geometry and quantum law, between the crossing of a falling traveller and the radiation of a dying black hole. At the horizon, darkness is not empty. It is a boundary of memory, and physics is still learning whether the memories it conceals are gone forever or only hidden in a language too subtle to read. The event horizon remains because every explanation returns to it. Black holes may begin with collapse, mass, rotation, radiation, and mathematics. Yet their deepest identity is still marked by this quiet threshold. It is not the centre, where classical theory predicts a singularity and quantum gravity is expected to speak in some future language. It is not the glowing disk, where gas can shine before vanishing from view. It is not the shadow alone, though the shadow gives astronomy a visible outline of the invisible. The event horizon is the boundary that gives all these pieces their meaning. Outside it, the universe can still receive news. Inside it, events continue, but their messages cannot return. That simple division turns a black hole from a compact mass into a causal region, a place where the structure of possible futures has been rearranged. The horizon is calm in one description and absolute in another, locally ordinary and globally final, a surface that is not made of substance yet changes the destiny of every path that crosses it. Its silence is part of its power. Many cosmic objects announce themselves through surfaces. Stars burn, planets reflect, nebulae glow, pulsars flash with regular beams. A black hole has no surface from which light can be emitted outward after the boundary is crossed. Its presence is known through effects around it, through orbits, heating gas, gravitational waves, and the bending of light near the edge. The horizon itself does not shout, it does not shine as a wall, it waits as a limit. This makes it unlike almost anything else in ordinary experience. The event horizon can be crossed without a local mark, yet it cannot be crossed back. Its strength lies not in impact but in absence. It removes a future rather than adding a force. It erases the outward route from the map without needing to touch the traveller at the moment of passage, from the outside. The horizon is a promise that will never be confirmed by a final signal. Falling matter appears to slow and fade, its light stretched and delayed until the crossing is hidden behind redshift and time dilation. The black hole can still grow, its gravitational field can still change. The larger universe can respond to what has fallen in, but no telescope receives a last report from inside. The event horizon therefore becomes a boundary between inference and direct knowledge. Physics can calculate its position. Astronomy can test its effects. Instruments can observe nearby plasma and the motions of stars. yet the inside remains beyond the ordinary cycle of experiment and answer. This does not make black holes unknowable in every way. It makes them knowable only through the part of their story that remains outside, and through theories whose consequences can be tested before the boundary closes. For the falling traveller, the same horizon is not a place of revelation. It does not display the entire future of the cosmos. It does not necessarily tear matter apart at the crossing. It does not need to glow or ring or harden. In a very large black hole, the passage may be smooth enough that only later, deeper inside, do tides become unmistakable. A local clock keeps time. A local lamp sends light across a cabin. Nearby objects still obey familiar rules in small regions. Yet this ordinary continuity now belongs to a hidden world. The traveller can receive some light from outside, but cannot answer beyond the horizon. The crossing has not ended experience. It has ended participation in the outside universe. That difference is severe. It means the event horizon is not death in the simple language of impact. It is exile by geometry, a division in causality where the future of one path no longer connects to the future of distant stars. The horizon also remains because it gathers unresolved questions. It is the place where general relativity appears smooth. While quantum theory asks what becomes of information, it is the place where entropy grows with area, suggesting that boundaries may count hidden states more deeply than volumes. It is the place where Hawking radiation gives black holes a temperature and a lifetime, changing the ancient image of perfect darkness into something more subtle. If a black hole evaporates, the details of what fell through the horizon must either return in delicate correlations, remain in some unknown form, or challenge the principles of quantum evolution. No settled answer yet closes the matter. The horizon is therefore not only a line of no return for matter, it is a line along which theories of nature meet and test one another. The mystery does not require exaggeration. A black hole is not a magic tunnel simply because some mathematical extensions contain bridges or extra regions. It is not a cosmic vacuum cleaner reaching across galaxies. It is not a visible hole punched into a flat fabric. Its real nature is stranger and more disciplined. It is a consequence of space-time curvature, speed limits, and mass compressed within a critical radius. It can be described by equations and detected by careful observation. It can merge with other black holes and send gravitational waves across the cosmos. It can sit in the center of a galaxy while stars orbit around it for ages. It can be small enough for tidal destruction to occur before the boundary, or vast enough for the horizon itself to be crossed in quiet. Each case changes the scenery, but not the central rule. Inside the horizon, the outward future no longer reaches the outside. This rule gives black holes their strange dignity. They are extreme, but not chaotic. They are dark, but not empty of structure. They are simple from outside, yet deep enough to trouble the foundations of physics. Their horizons are invisible, but they organize space, time, and knowledge around them. Every falling photon, every grain of dust, every broken star, every theoretical observer must obey the same causal geometry. No special substance is needed at the threshold. No dramatic surface has to appear. The event horizon does its work by being the last place from which a light signal can still belong to the external future. Cross beyond it, and the cosmos outside becomes unreachable, even if its light still falls inward for a while. The universe has not disappeared. The route back to it has, at larger scales, horizons also make black holes part of a wider family of cosmic limits. The observable universe has a horizon because light from sufficiently distant regions has not had time to arrive or may never arrive because of expansion. Cosmology and black hole physics both reveal that observation has edges, not always made of matter, but made of causality. The black hole horizon is the most concentrated and severe version of this idea. It shows that the universe can contain real events forever excluded from outside witness. This is not a failure of instruments. It is part of how space-time can be arranged. The event horizon teaches that reality may be larger than what can be reported, and that existence and observability are not always the same. The final image is therefore not a roaring mouth in space, but a silent border drawn by the laws of motion and light. Around it, matter may blaze. Far from it, galaxies may continue their slow turning. Inside it, paths continue toward a hidden future where known theory grows incomplete. The horizon itself remains between these worlds, neither solid nor unreal, neither an object nor an illusion. It is a threshold that can be crossed only in one direction, a border whose local quietness makes its global force even more profound. The question of what happens there has no single dramatic answer, because the horizon is many things at once. It is where escape ends, where outside observation fails, where falling time continues, where light cones turn inward, where information becomes a problem, and where the known universe accepts that some stories have no returning signal. In the calmer sense, the event horizon is the edge of a promise that physics keeps perfectly. Nothing outruns light. No influence travels outside its allowed future. No message escapes from a region whose causal paths have turned inward. From these simple rules comes one of the strangest objects in nature. The horizon does not need to burn. It does not need to announce itself. It only needs to mark the last outward possibility. Beyond it, the black hole interior carries on beyond sight, holding whatever has crossed in a silence that is not empty, but unreachable. The surrounding universe continues, changed by the hidden mass, lit by whatever remains outside, and still unable to hear from within. At the event horizon, the cosmos reveals a kind of boundary more absolute than stone and more subtle than shadow. It is the place where return becomes impossible, where knowledge becomes partial, and where the deepest mysteries of gravity remain quietly open. Beyond the event horizon, the story does not close, it recedes. The black hole remains in the universe as a dark punctuation in space-time, a place where gravity has shaped the future into a one-way path, and where light itself accepts the inward turn. Around it, stars continue their long burning. Dust drifts through galactic arms. Radiation crosses ancient distances. Far from the horizon, clocks keep their ordinary rhythm, and the wider cosmos carries on with its slow expansion, its merging galaxies, its forming worlds, its quiet fields of darkness between light. The black hole does not explain itself from within. It leaves only traces the motion of nearby stars, the glow of matter not yet lost, the ring-like shadow of bent light, the faint tremor of gravitational waves after two horizons become one. Its deepest interior remains beyond reply. Yet that silence is not emptiness. It is a reminder that nature can contain regions where events are real but unreachable, where knowledge has a boundary set not by weakness of instruments, but by the structure of causality itself. The event horizon stands as one of the calmest and most absolute ideas in physics. It is not a wall, not a surface, not a visible wound in space. It is the last outward possibility, the final line between a story that can still be shared with the cosmos and a story that continues inward alone. At that threshold, the known laws remain elegant, but not complete. Gravity, quantum theory, time, and information meet in a darkness that still asks for a deeper language. Until that language is found, the horizon waits without motion, holding its mystery in perfect quiet, while the universe around it turns slowly through the night.